So, good afternoon. We will start with a new topic. It's called as the order statistics. So, this will often you will encounter a situation where we can make use of this concept and solve certain problems. So it's a different unit or a discussion by itself, and but you will find it will be useful under certain circumstances. The situation is like that. We have a collection of IID random variables. We will denote it as x1, x2, x. Okay. So then what you do is you do the random experiments and then get the realizations of these random variables. So let us denote by small case letters the realizations of these random variables. Okay, and then what you do is you arrange the realizations in an ascending order or in some order. You look at ascending or descending, can be different ways of doing it. It doesn't matter. Both of the discussion will be the same. So arrange the realizations in ascending order. Then you will get some values. Let's denote that as this is the realization. After arranging it, it will change. That I will denote it using this notation y1, y2 to y2. By that what we mean is y1 is equal to the minimum of x1 to xn. Yn is the maximum of x1 to xn. And then y2 is the second minimum. And similarly, you can think of yi with the ith minimum. Well, you can associate random variables to all these things. In the sense, I can tell that y1 is a random variable that represents for the minimum of n realizations of IID random variables, and after getting this realization and ordering, I would get the realization of y1, capital Y1 or small y. And yn is the maximum of the random variables x1 to xn. How do I find a realization of y, capital Yn? I conduct experiment and get the realizations of capital X1 to capital X1, which are small x1 to xn. Then order it, find yn. That would be the realization of capital Y. That way we can do it. So these will be random variables. y1, y2, y3 are all random variables whose realizations are like this. But you cannot just find y1 alone. To find that one, you have to get a realization of n, all the random variables, order it and then get it. Okay? To give an example, suppose x are all uniform integer random variable between 0 to 100. So if you look at the x PMF will be like this. 1 over 101 also. So it takes integer values lying between 0 to 100, and we have n such random variables are all IID. Their common PMF is what I have given. So x1, 2. Let us take 5 of them. And then we will consider a realization. One such experiment that leads to 5 realizations of these random variables. The possible numbers can be, for example, I may get a 13 here, then 52, 93, and then 7, and then let us say 65. Okay. These are the realizations of this one. That is, this is the x1, this is the x2. Then what I do is I order it. That would be, so first I will get 7, then 13, then 52, 65, and then 90. Then this, whatever that comes, that is what I will call it as the random variable capital Y1, whose actual value turns out, small y1 turns out to be 7 in this experiment. And this is what I would call it as y5, which is the maximum of x1 to x5. So what is y1? Mean of x1 to x5, and y5 is max of x1 to x5. In a similar manner, other things are being can be reached. Now, what can you tell about the characterization of y1, y2, y5? The support will be the same. What do you mean by support of a random variable? The values that it can take. It will also lie between 0 to 100, because they are all nothing but some numbers only. What x1 can take, the same value only y1 can take. Will it be uniform between 0 to 100? y1 and y5. Can I say yi is uniform 0 to 100? Is the question clear? x1, x2 or x3 are all uniform 0 to 100. And then I take realization. And then order it and take the minimum. Now I ask why that y1, which is the minimum of 5 of the realizations of uniform distribution, will have what distribution it will have? What PM of y1 will have? It will be uniform. Think about it. See, what I do is, let us take here, you change the rule, we have 1000 randomly, 1000 realization and then take the minimum. Do you think still 99 is very probable? As probable as what? No, it is 1000 values randomly you put from 0 to 100 and then you take the minimum. For 99 to happen in that one, all the 1000 numbers which you have taken realization has to be either 99 or 100, which is very unlikely. So it will not be like that. It is very likely you will take values in this range. y5 is very likely to take values in this range. So it will be it has to be skewed, because one is minimum, another is maximum. So this is what we are interested in. This is quite commonly you will encounter these things. What you do is you conduct an exam and then entrance exam or something, some marks are obtained, you are interested in what will be the minimum value that you will get, what will be the maximum you will get. Not only that one, you want to, let us say, select 30% of the candidates who wrote the exam for the job also. So you will be interested in what will be the sum out of 100, 30th. One will be the y30 will be the 30th minimum out of 100 marks that you have got. So where will that be? You want to put the cutoff of the mark for selection based on that. So all these, that is why all these, not only the minimum and maximum, any other thing is also important. We will call all of them as order statistics. Okay, order because you are ordering the random values and from a statistical point of view you are looking at it. Well, now this x1, x2, all these things can have identical distribution or it may not have. But one thing you are assuming they are all independent. If they are dependent, it will become very complicated. We will not even get into that. They may have identical or non-identical distribution. Again, for simplicity, we will assume they all have identical distribution. Okay? So, which means that x is a random variable. Any random variable it can be. We will not even confine to any particular, whether it is integer or continuous and so on. We will again, because we will assume its density function is denoted as fx of x and CDF density function is given by this. I should have introduced sometimes. We can also have mixed random variables where it can take values are over a continuous range and sometimes specific values. They are called mixed random variables, valued random variables. But you can always, if you have a random variable which takes only discrete values, that can also be treated as special case of continuous valued random variable by including direct delta functions. Okay, what I can do is, for example, delta of x minus x1, which means that only when P2 property P1, like that I can always write it. That is, this is a general, it's a function, generalized function because it's a direct delta function. So with property P1 it will take a value x1. So if another value x2 is taken, it takes the property P2. So this kind of a function, if you write it, a PMF can be treated to be a continuous function. It takes only at specific values. So that is why without loss of generality, we will look at continuous valued random variable. So this is given, and they are also IIDs. Now, how do we arrive at y1 and yn? That is something which should be easier. What is y1? That is, y1 is something that we have done after ordering. Minimum of x1 by xn. And yn is max of x1 by xn. And all x are all IID with fx of x and as the density function and the CD. Now we want to characterize y1 and y2. We will start with the y1. Okay. So what do we mean? We want CDF of y1. How do we denote it? That yn of y. I could have put small n here also, but I will not bother. It's only a dummy variable. It does yn taking less than or equal to y. How do I write it property that yn is less than or equal to y? This we will try to find. Again, what we will do is we will write the definition of yn in this place. What is the definition of yn? Max of x1 to xn less than or equal to y. Right? Because yn is max of x1 to xn less than or equal to y. So you look at this condition. Maximum of x1 to xn has to be less than or equal to y. which means that x1 has to be less than or equal to y, x2 has to be less than or equal to y, and so on. Then only the maximum itself will be less than or equal to y. Clear? So, write your value as probability that x1 is less than or equal to y, x2 is less than or equal to y, and so on, xn is less than or equal to y. So, f yn of y is equal to this one. But x1, x2, xn are all independent random variables. So, this PMF or the total, this probability becomes a product of individual probabilities. And that is what? They are all individual CDFs. Product of individual CDFs. F x1 evaluated at y, f x2 evaluated at y, evaluated at y. And if they are identical, see this up to this one we have not used it. We have only used the independence condition. From here to here we have used independence. If you also use identical, then all are same. That is what we denote it as f common fx. F but evaluated at y, that is important. Evaluated at y, at that you want the CDF value of yn. How many? Okay. So, getting the maximum is quite easy. Okay. Similarly, getting the minimum will also be easy. But getting the statistics or the PDF of an arbitrary value yi will need little bit of thinking. Now we will look at the other one, f y1 of y. I won't have much space here. We go there. Right. Again, what I do is, what is this one? See, all the time what you do is you have to only, you go to the first principle. If you write something, then you write what is the condition. Then you apply your logic and then slowly build upon it. That's it. This is what you have to do. But now if I straight away put instead of max, min and so on, I will find it difficult to proceed further. So what I will do is, x equal to 1 minus probability that y1 is greater than y. That will be equal to 1 minus probability that min of x1, x2, xn is greater than y. So here, before that, if you want, you can come why we are writing it like this. See, what we are doing is, let us say, this is the range, suppose for all the random variable sets. You can take only values in this. So x1 can be, if you, it may take a value like x2 can be like this, x3 can be x4, x5. Something like that randomly it occurs like this. And this will become the minimum, this will become the maximum. This is how it occurs. Okay? You are asking, what is the probability that the maximum occurs at a value y? What is the probability that the maximum occurs at y? Then it means that what should happen is the y1 has to be less than y, x1 has to be less than y, x2 has to be less than y, everything has to be less than y. Then only the maximum itself will be less than y. And that is how we got this. In the case of minimum, what is the probability that the minimum occurs here? Then everything has to be above this. So minimum of x1 to xn has to be less than y, which means that x1 should also be greater than y, x2 should also be greater than y, then only its minimum will be greater than y. Okay. So if this is where y is, then everything should be on this side. Then only the minimum itself is greater than y. So everything individually they have to be greater than y. Again, all of them are independent. So this is 1 minus. What is this quantity? This is the CCDF, complementary cumulative distribution function of x1, x2 and so on. We invoke the assumption that they are also identical. Okay. So, deriving the CDF of minimum and maximum turns out to be very rather easy. Now we will look at the generic one. So for that, henceforth we will use a notation, proper notation. Let's take n, we will only stick to IID random variables. Independence is required, identical is also, E makes it easier, and that we will confine to only order statistics of IID random variables. And without loss of generic, we will take it as n. So n IID random variables, which we will denote it as x1, x2 to xn. And then, if you take a realization and then find the minimum of that one, that we call it as y1 and so on. Let's not introduce another notation, y and so on, because they are all what they are length, they are ordering of these random variables. So we will use the notation x1 within a bracket to be the minimum of x1 to x. Similarly, xi to be the ith order statistic. How do we call it? Ith order statistics of x1 to xn. What we really mean is it is the ith minimum or n minus ith maximum. It's a verbal one, you should clearly understand what it means. Ith minimum means the second minimum, third minimum, ith minimum. And xn is what? Maximum. Yeah. So this is the notation that we will follow. Henceforth, in any book you refer, or in exam whatever question that if you moment you find this kind of this, it means it is an order statistics. That is the subscript written within a bracket means it is the corresponding order statistics of a collection of certain random variables which has to be mentioned. So we found the characterization of x1 and xn. We will look for I. that one, we will use the elementary formula from basic probability, which is the formula for the multinomial distribution. I think I also introduced it. We also looked at it, but we will recall because we are going to basically make use of that. Okay? So we know what is binomial distribution. That is, if you have n trials and probability of success is p, then probability that random variable x takes a value k is k successes out of n trials, n choose k, probability of p k successes p power k, 1 minus p power n minus k. This is how we will get. And what is this one? This is, and so there are only two cases, success or failure. So you have this form of n factorial divided by these two one, and whatever that comes here comes as the exponent of that corresponding one, and so on. Well, now we have got a multinomial, that is, there is not just success and failure. There can be 3 possible outcomes or 4 possible outcomes. And you can specify the probability of each of these outcomes. Okay. So you do n experiments, and out of it you will expect n1 of first outcome, n2 of second outcome, and so on. To be a little bit more specific, let us say you have a certain number of balls. Okay. So you have got n balls, and you know the composition. So you have, let us say, we will take green, red and blue. N1 green balls, N2 red balls, N3 blue balls. So that N1 plus N2 plus N3 is equal to n, the total number of balls. And you pick n balls, and then let's not take n1, n2, that is not required. We will find whatever it is, and then I have found out that the probability of, if I arbitrarily pick a ball, the probability that I will get as a green is p1, which will be again n1 by n only. I want to reserve the notation n1 for later. So probability that I will, when I draw a ball at random, it will be a green ball with probability p1, red with probability p2, and this one. So accordingly the equation is p1 plus p2 plus p3 equal to 1. Now I draw n balls, out of which I am looking for n1 green balls, n2 red balls, n3 blue balls, and you know the corresponding probability will be n factorial divided by n1 factorial, n2 factorial, n3 factorial, p1 power n1, p2 power n2, p3 power n. Okay? So this is the multinomial distribution. We will make use of it in order to derive xn. So xn is what we are interested in. So we will look for the density function of this one. 1 minute. Yeah, we have also, we can not only stop with CDF, we can even proceed and then get the density function. If we write it, for example, what we did is x f yn of y, whatever we have got, yn, y is fx of fx at evaluated at y power n is what we have got. So if you want fyn of y, the density function of y, which is d by dy of fyn of y, that is again differentiated with respect to small y. So n fx of y power n minus 1 into fx of x evaluated at y. See, it is not one, what it means is I find fx of x and then substitute y. That is what I have written. It is not here fx of y. Fx of y is the value. Okay, after substitution itself I have written it like this. So you differentiate it and then substitute y in these two places. So this will be the density function of y. In a similar manner, you can differentiate and get the density function of y1 also. Yeah, this is what we are looking for. So let's say this is the support for x. What does it mean actually? How do we interpret it? Probability that xi lies between x and x plus dx is equal to fxi of x into dx. To get the probability that the ith minimum lies in an interval x and x plus dx can be found out by multiplying the density function of fxi at x by the interval size dx. That is, if this is the range over which x's can take value, which means that many realizations may take values like this, but the ith one should lie in an interval x and x plus dx. What is the probability it will happen? That's what the question is. So, if the ith, see, this is already in order, okay? After realization, if you look at, this is the smallest, this is the largest, and so on. The ith one should fall in this one. How can it happen? The smallest one has to be less than this. Up to I minus 1 has to be less than this. But it can all be centered at this place, that's also allowed. Or it can all be here, or it can be spread out. As long as they are all less than this point, it is smaller. And ith one has to be in this small interval. And then the remaining, which is n minus I, has to be greater than this one. So if this happens, then xi it will have a value in this place. I have to find the probability of that. So, I minus 1 should lie in this interval, and then the ith one should lie in this interval, and then n minus I should lie in this interval. This is what should happen. What is the probability that a realization will happen to be less than this, less than x? Huh? Fx of x, capital Fx of x. And what is the probability that a realization, which will happen to be the ith one, will lie in this interval? That will be Fx of x into dx. What is the probability that a realization will lie above x plus dx? Again, all of them will have the same probability, but they have to be n minus I should have that will be of that kind. That is nothing but Fx of 1 minus. Right? plus dx. This is what will happen. So now the problem is very simple. Okay, I am throwing some balls like this one, or dot over this one. The probability that it falls in this place is this. Probability it falls in this place is this. Probability it falls in this place is this. It's like drawing ball, out of which I want I minus 1 green ball, only 1 red ball, and remaining all whatever that color maybe. That's what I am looking for. The same probability equation will also hold here. Okay. So, but out of n, I minus 1 has to be chosen, which has to be here. 1 has to be chosen, which has to be here. N minus I have to be chosen, which has to be here. There are different ways of doing that one. And that probability is n factorial divided by I minus 1 factorial into 1 factorial into n minus I factorial. This whatever you have got. Okay? Because I minus 1 should be less than this particular point. And the corresponding probability P1, P2, what are P1, P2, P3? P1 is this, P2 is this, P3 is this. Okay. So, this fx of x into dx is equal to this into fx. They are all identical. Fx of x is the probability. How many of them has to be, should have this one? P, this is P1, power I minus 1. And the probability that the ith one will fall in this interval is and probability that n minus y will fall in this interval is this probability power n minus 1. Now what I am doing is, the interval is going to be smaller, very small. So this we can as well put it as fx of x itself. So this is the probability that xi will lie in this interval is, okay, I minus 1 lies less than x. 1 will fall in that interval, small interval. N minus y will fall above the interval, beyond that point. And these are CDF and CCDF gives you correct simply those probabilities. This is what happens. Now, this is the equating these two probabilities. Now I want only the density function. So I can drop these two things. In terms of density function, this and this can be struck off. And the density function of fx of x is that nothing but this. Okay. So this gives you the density function of any order statistics, ith order statistics. Now, if you want the joint density function of the ith and jth order statistics, how do we find? See here what happens here, because it is a continuous valued random variable, no two realization will have exactly the same value. They will be separated by some infinitesimally smaller interval. So ordering is always possible. Tie will not occur. But if it is an integer one, tie can occur, then you have to properly define what you mean by the order status. If two values same this one, which one will you put it as the lesser one, and so on. So what will, again ith and jth, what we will take, okay, I less than j. That is, for example, you have 10 random variables, you are looking at the joint density function of the third and seventh minimum. Third minimum and seventh minimum is joint distribution. That is, third minimum taking a particular value and seventh minimum taking another value. So again, you look at this, this is the support. I look at different realizations, but the third minimum has to be here and the seventh minima has to be here. And it can be anywhere, third and seventh can be in any place, but third has to be prior to seventh, that is obvious. Okay. So if that has to occur, then what should happen? If third has to occur, 2 should be in this side. If seventh has to occur, 8, 9, 10 has to be this side. And 7 minus 3 has to be in between there. The same thing we can apply it for this one. So if this is the ith one and this is the jth one, so I should have I minus 1 on this side. Then the ith one here, jth one here. So below this point j minus 1 has to be here. Below this j minus 1, then only this will be j. But I want this interval. How many will be in this? How many will be that? How many will be in this interval? J minus? But here it has to be j minus 1. J minus 1 minus 1. You can easily see that. See, j at this point j should have occurred. I minus 1 plus 1 I plus j minus 1 plus 1 I plus j minus I j. J has occurred. And how many in this place? N minus j. So if this occurs, then the ith one will take this value. Okay, we will call this as xi. This is x. So we are interested in finding the joint density function, which we will denote it as here we have used the order statistic notation. By that we mean probability that okay, xi plus dx, and this is what we are interested in. So for this to occur, what I will do is I will split the points that I am throwing here. I minus 1 should fall here, 1 should fall here, and so on. So it's just a multinomial distribution. So n factorial divided by I minus 1 factorial. Why we are doing it? We can find the probability one way in which I minus 1 fall here. That is fx of x over I minus 1. And all those things we can get. But the number of ways in which we are occurring, that is what we are writing it using this. There are many ways in which I can pick I minus 1 and put it in this place. N minus I put it in this place. And that is what this factor gives. Into 1 factorial into j minus I minus 1 factorial into 1 factorial into n minus j factorial. Into what is the probability of anything falling in this place? Anything falling less than x, xi. This is the xi. This value is xi. It is fx of xi. And this you know, this is small fx. Yeah, it's the same small f because the density function is the same. And so, what is this value? One minus fx of xj. This is xj. It is the CCDF evaluated at xj. Then only this will be on this. And what is this? Anything that falls in between xi and x2, xi and x2. What is the probability that a dot that is being thrown will fall in this? Yeah, it is fx of xj minus fx of x. If the subtraction of CCDF evaluated here minus CCDF less than or equal to this minus less than or equal to this. So then we have got fx of xi power I minus 1 into fx of xi into fx of xj minus fx of xi power j minus I minus 1 into fx of xj into 1 minus fx of xj power n minus 1. So this is what would be the joint the density function of xi and x2. Similarly, you can joint density function ijk, you can find it and so on. Ijk, if you want it, three, we have to put three of them. You have to find accordingly, to find the probabilities and then use the multinomial. If you want the joint density function of all order statistics, the formula turns out to be little easier than this. That is f of x1, x2 to xn of x1, x2 to xn. That is the minimum taking this value, the next minimum taking this value, and taking value at those points, around those points, because this is a density function, and this is what you are learning. So that is what we mean by that is, if you tell that this is where I want, tell me the probability means that the x1 has to be here, x2 has to be not x1, the order statistics has to be here, like this one. So it is nothing but, here you don't have, see here there is nothing. See, the same way, I am telling the place of all n of them. In between there is nothing. If you find that one, it has to be power 0 has to be put. So those things will not come at all. The CDF and CCDF will not come. So it is just by fx of xi, fx of xj into fx of xi. I have to just find this because I am equating densities. That is why I am not putting dx, dx, dx and all this. When probabilities are equated, you have to multiply it by dx. This density is this. Fx at this point. But something else, there is something more to it. What is it? This is not the right formula. For this to occur is, one has to fall here, one has to fall here, and the density of falling is fx at xi, fx of xj and so on. That is right, huh? Yeah.
X2 can be the first.
Yeah, you have different ways of choosing what falls here, what falls here. How many ways of choosing that? N factorial. It is just without replacement. I can, out of n, I can decide one of them to go here. After that, I have only n minus 1 choice to go here and so on. So it is n factorial. So n factorial times this. Again it comes here, what happens? These are all, nothing should fall in intervals. These are all 0 factorial, this is 1 factorial. That is why all these will go away. So the n factorial alone remains here. These things will not come. Only these things are coming. That is what is happening. These things will not come at all. Okay. So this is about the joint statistics. Now we will take an example. For example, x is uniform between 0 and 1. Okay. For that you know what is the fx of x. This is 1. Right? Because it is like this. And then fx of x. For uniform distribution, what is fx of x? That is the CDF x. But let me not put 0 and 1. I will put it as 0 or t. Make it little general. Okay? Then it will be x by t. T is the interval size. Because CCDF will go like this. Whatever from A to B, if you put it or 0 to t, CCDF will go like this. It will be linear, so it will be x by t. Between this one, it is 0 below it or 1 above it, or 0 and 1 below and above. That's how we know. So now we can, for this we can plug in these formulas and then write out. So if you have x1 to xn, they are all uniform 0 to t, random variables. I want x of n. What is it? It is the maximum. What is the formula? Yeah. This is the formula for maximum. That is simply x by t whole power. That's it. And minimum. That will answer the first question which I have asked. Is 1 minus of 1 minus fx of x whole power. That will be 1 minus of 1 minus x by t whole power. This is what we have. Okay? This is what we have. In a similar manner, you can put it for other things. This is for the other one. Okay. It will not. This will not be uniform at all. It will be very different. Finally, I have finished off with only one thing. We have x can be x4 random variable with parameter lambda. Okay. In general, x1 to xn can be x4 with respective parameters lambda 1 to lambda n now. Then, if I want to find x1, that is the minimum, to be very specific, minimum. Then what is it? It is 1 minus of 1 minus fx of x power n. What is the CCDF of probability that x1 is greater than x? Where x1 is lambda, you see exponential with lambda. It is nothing but e power minus lambda 1x. Lambda 1x. Probability that x2 is greater than x is e power minus lambda 2x, and so on. So, if we have n exponentially distributed random variable, and then you want to find the minimum, what is the use? We have n bulbs, all same lifetime, exponentially distributed. You fit it. You want to know when will be the first bulb go away. So that is nothing but 1 minus r. 1 minus fx of x is what this one is. E power of minus lambda 1x. Okay? But this is when they are all identical. If they are not identical, it will be 1 minus fx x1 into 1 minus fx x2 and so on. Like that. That is equal to 1 minus e power of lambda 1 plus lambda 2. Yes. This will be, what is this? This is the f, the this is the t, actually this is the CCDF of x1, which is the probability that x1 is greater than x. That is, the lifetime of the first one to go away itself is greater than x. Sorry, the x1 is less than or equal to x. It is given by this. Which means that you will see that, see, this is the familiar formula for the CDF of an exponential random variable. The only thing is the parameter is this. Okay? So, x1 is also x4, but the parameter becomes lambda1 plus lambda2 plus lambda n. Which tells that if we have n exponential random variables, the minimum of them is also exponential, but the parameter is the sum of the individual parameters. If they are at the same identical distribution, it becomes n lambda. If you interpret lambda to be the failure rate of one component, if you put all them into use and then ask for which is the first one to fail, its failure rate will be n times the failure rate of this. Okay, we will stop it.